this. We're going to use contingency tables to evaluate conditional probabilities. So we have a rule here that says the probability of B given A, that's what that vertical slash means, given, is equal to the probability of A and B, so there's the and symbol, over the probability of A. All right, so in the form of a table, we would have probability of, well, in this particular case, it's a table that shows the results of a survey of 100 randomly selected people entering an amusement park who were asked whether they were planning on riding the Monster Loop roller coaster. All right, so we're looking for the probability of yes given ages of 16 to 25. So what we need to do is match this up against the formula, all right, which is the probability of B given A is equal to the probability of A and B over the probability of A. So that means that B is taking on the role of yes, and A is equivalent to ages 16 to 25. So what this is really becoming is the probability of ages 16 to 25 and yes. All right, and that's going to be divided by probability ages 16 to 25. All right, so the and here is really crucial because that's telling me that I'm looking for the intersection between the column associated with 16 to 25 and the row corresponding with yes. All right, so there are 23 individuals who are ages 16 to 25 who also said yes, out of the grand total, which is 100. So 23 out of the 100 people surveyed were in the 16 to 25 category, and they also said yes, that they were planning on riding this roller coaster. All right. Now the probability of just a person saying that they're in the 16 to 25 category would be 34 out of the 100, which simplifies down to 23 out of 34. Now, if I want to look at this, in a little simpler fashion, what I could do, I just jotted this down here, is actually consider it in a more literal sense. Probability of yes, given the person is in 16 to 25. It's really just a verbal representation of what was there symbolically, right? But if I look at that and say, it's a given fact that the individuals are in the 16 to 25 category, what I could say is, let's ignore every other part of this table except for the 16 to 25 category, because that's the given, all right? These 23 people said yes. These 11 people said no. And this would be my total. All right, so if I'm looking for just out of this category, who said yes, there are 23 people who said yes. There are 34 in total. That's what we came up with over here. All right, so you can do conditional probability without having to make a really complicated expression. All right, so with that being said, I could look at this and say that for number 2, we're looking for the individuals who said no, given that they're in the ages 16 to 25, 16 to 25, just did that, the 26 to 35 category. All right, so this is my given. So in this one, this would be my given. So now I'll just take this stuff here and slide it on over. Yes, no, total. All right, so now I'm looking for the no's. So there are 12 people who said no, out of the total for the given, which is 20. All right, so whatever the second thing is, that's going to be your given statement. All right, for number 3, it now changes perspective. So now my given is just the people who said no. So let me get rid of all this. Hang on to it in case I need it later. So just the people who said no, that's my given. This would be my total. Now I'm just looking for the people who are in the 26 to 35 category. All right, so this is the number of relevant people, or 12 of them, out of the people who said no, which is 46. Number 4 says which is more likely. Yes, given that you're 36 or older. All right, so let me use my handy dandy highlighter. So the given is 36 and older, so that puts me right here. So out of the individuals who are 36 and older, that's a total of 29 people. How many said yes? 14. Let me get rid of this completely. The next one, or the next part of it, yes, given that you're in the ages of 8 to 15. So let me take my highlighted rectangle here, go to 8 to 15. How many said yes? 9. How many were there in total? 17. You want to know, are these two equivalent to one another? Just run it through a calculator. 14 divided by 29, about 0.483. 9 out of 17, 0.529. So these are not equal. All right, so we can answer the question of which is more likely. This one is more likely. All right, if they were the same, then I wouldn't be able to answer the question. If they're different, that's how we know that we can actually answer the question and decide which one is more likely. All right. Now, the last question here involves making a table. All right, so they give you the words, and you got to make it a table so you can answer the question. All right, so in a sample of 40 vehicles, 18 are red. So red is 18. 6 are trucks. And 2 are both. All right. So that tells me that there are 2 vehicles that have been accounted for in both the red category and the truck category. So I have to subtract that off. All right, because it didn't say that the 18 are red but not trucks. They said that they're just red. So some of those trucks are going to be in there. And it's in particular 2 of them. So I'm going to knock off 2 here. That's going to give me 16. I'm going to knock off 2. That's going to give me 4. All right. So a car that is a red and a truck, there's 2 of those. Red but not a truck, that would be these 16. Trucks that are not red, that would be these 4. There's 40 vehicles overall. These 2 numbers add to 18. So this one must be 22. Which means that this has to be 18, 34, and 6. So now we could use it to answer the question. If it's given that it's red, what's the probability that it's a truck? 2 out of 18. If it's given that it's not red, what's the probability it's not a truck? There's 18 of those out of 22. And lastly, if it's given that it's a truck, so that's all of this, what's the probability that it's not red? 18 again, but this time out of 34.